Welcome to the last lecture of our first module. This lecture is dedicated to quantum circuits and more specifically how we count the cost of a quantum algorithm, and will serve as a basis for the future more high-level lectures on non-trivial quantum algorithms. So time evolution of our quantum system, of our qubits, or systems of qubit, is really important here, because the whole point of an algorithm is to take an input state to an output state that hopefully, whose measurement hopefully yields the solution to a problem. The very important postulate here is that evolution is a linear process. What it means is, if you know the evolution on every one of the basis states, then you will know, by knowing that every arbitrary state is a linear combination of the basis states, you will know by linearity of the evolution of any state. So that's a very powerful postulate. And we even specify that for a closed quantum system, which is really the kind of systems that we'll be interested in, the evolution is actually a unitary operator. Remember, unitary matrices are the ones that are self-adjoint. Unitary operators are those for which the adjoint is the inverse. Now, first example of those matrices that are going to be featured in our time evolution of a system is the Pauli group. So the Pauli matrices are the identity and the matrices that we will denote consistently across this course, X, Y, and Z. So these 2x2 matrices, I will leave it as an exercise to verify that they are unitary, and they form the Pauli group, which is a finite group made of the multiplication of all these matrices, okay? Now, from there, we will define a more general group of matrices, the 2x2 matrices. And again, this will serve as a description of arbitrary evolution. But for now, these are very specific evolution. Those matrices that form the Clifford group, so another class of unitary that encompasses the group, but is actually more general because it's defined as all those matrices such that if you conjugate them, if you use them to conjugate a Pauli matrix, it stays in the Pauli group. And it turns out that this group, the Clifford group, can be generated by the Hadamard matrix and this phase shift matrix, whose square winds up being the Z matrix. So that's the sort of smallest generating set that we can come up with. And here is why this is all important. It turns out what we want as an analogy with classical circuits is a small set of operations that can make up for any arbitrary circuit, any arbitrary algorithms, okay, that can implement any evolution, right? So here's the thing: with classical circuits, we can work, for example, with only the NAND gate and recreate any arbitrary algorithm. It turns out here the situation is a little bit more complicated because we're looking at unitary matrices, and you cannot just generate every unitary matrix out of a small set of matrices. But the next best thing you can do is approximate them. See, everything is only probabilistic. So if you have a matrix that is close to the unitary operator that describes the evolution of your system, then probably the measurement at the end of this approximate operator will be very close to the measurement you would have had with the ideal operator. And that is, if the precision is good enough, then this is pretty much, this will be good enough as well. Now, the Solovay-Kitaev theorem tells you that if you have the Clifford group, if you have generators for the Clifford group, and the T matrix, the T gates that is defined here, then with this set of so we call them gates because we'll talk about circuits, but for now, let's call them matrices. But with those sets of matrices, we'll be able to approximate any arbitrary unitary operator with a very good precision. Now, what does it say very specifically? Suppose you have a precision epsilon to which you want to approximate a given unitary operator u, then you can create a product made of HST matrices such that the length of the product, so the number of terms here, is going to be a polynomial in the log of 1 over epsilon. So you see, of course, that the smaller epsilon, the longer the product. Okay, so that sort of explains the dependency in 1 over epsilon here, and such that the difference, the distance between those two terms is going to be less than epsilon. So you will be approximating, you can approximate any given unitary operator on 1 qubit by a product of h, s, and t that is short with respect to the precision that you're requiring. Okay, so that's a powerful statement. An interesting consequence, of course, is that if everything you want to do, the evolution you're trying to reproduce here occurs only on 1 qubit, then it will be efficient. Now, of course, we're going to have to do operations on multiple qubits, so we'll have to add some gates here that will sort of take 2 qubits and sort of bring together the information on 2 qubits. So what is it going to be? So first of all, before we get into that, we need to talk about the way we represent our quantum circuits. So this is a form of diagram that we'll be using throughout the course. We will put in a box a sort of description of the operator that is being implemented. So typically you could have HST in there, but also we will use a more generic notation every time there's a unitary operator. It will be represented, even if it's on more qubits, it will be represented by a box with a description in it. And then the diagram represents the evolution from left to right. So here you have your incoming state of an alpha 0 plus beta 1, and then this is the outcoming state, okay? So this kind of diagram we'll be using throughout the course, and yeah, so we assume that, so that's for 1 qubit, but sometimes we'll generate it for several qubits, as we're gonna see in what follows. So here is your diagram for multiple qubits. So here, like I said before, everything is happening on 1 qubit, but we're just looking at them together. Later, after this slide, we'll have to discuss what happens when we actually want to make a computation that involves multiple qubits. Here, all those qubits are acting independently. So this is how you represent a diagram where everything is, so where you have 3 qubits. This is the first one, this is the second one, and this is the third one, okay? And here you have for each line, each wire, we'll talk a lot about wires in this course. For each of these wires, you have the same sort of evolution that I described before. And then another way that this can be seen is that altogether, this is an operator on 3 qubits that is described by the matrix that is the tensor product of operators H, I, and I. So the identity here, of course, because there is nothing on the wire, so this is an identity matrix, okay? And so this is the 8 by 8 matrix that represents the action here on the 3 qubits all together. And likewise, you can describe what happens in slice 2 and the slice 3. The slice 3 seems to be the most intricate because it has things happening on every one of the wires. And then, of course, the evolution is given by slice 1 times slice 2 times slice 3 on the 8, the vector of 8 coordinates that represents the input state. Now, here is one of the most important sort of gates in quantum algorithms is the Cnot gate, because this is what realizes entanglement between the wires or the qubits. So previously I showed you the kind of general design that we're using, but this was occurring on independent qubits. You can probably intuitively imagine that nothing very interesting will happen on independent qubits. Okay, we can do everything that involves one qubit efficiently due to the Solovay-Kitaev theorem, and then we can certainly do them independently on non-interacting qubits. However, every operation that involves multiple bits of information will require the qubits at some point to interact with each other. And this is, so we'll have to throw one more gate in our gate set to approximate efficiently any arbitrary circuit. And that is the Cnot gate. Now, other gates could do it, but Cnot plus Clifford plus T is really, I think, the most widely used, widely referenced gate sets, but it is not the only gate set you can use, but it is the one that we'll be using and referencing throughout the course. Now, the Cnot is performing the following operation. So first of all, the diagram for the Cnot is this. So this is on the top, the control qubit, and on the bottom, the target qubits. And what happens is, if you have a 0 and a qubit given by A, where A is 0, 1, then at the end you'll have 0 and A. So when the control qubit is 0, then nothing happens. But on the other hand, if the control qubit is 1, then what will happen to the target qubit is a XOR. So here you have this behavior. And that is what the Cnot gate does. So controlled not, controlled by the control qubit. Okay? So as an example, here is what it does on this particular state here. Assume that you have this product state. Now, this product state, in terms of quantum mechanics, this is, because it is a product state, we're talking about two qubits that do not interact. Okay, that is our postulate. This is what the product states describe. Now, let's see what happens once they go through the Cnot gate. Through the Cnot gate, by linearity, you'll have that Cnot of that state is the sum of these two things, and then the Cnot of 0, 0 leaves it like this, while the Cnot of 1, 0 will turn the 0 into 1, and then we get our completely entangled state here. So what we've done is we've taken a product state, we sent it through the Cnot gate, and we obtained an entangled state in the end. So we see that the Cnot is this essential tool that will realize entanglement between the qubits. Okay, and it's pretty easy to see why it should be necessary to have in our circuits. Now, to think about in terms of the physical realizations we've seen in the introduction, the Cnot is a little bit like this beam splitter we saw, where that was realizing entanglement between the state of polarization and the state of momentum of the incoming photon. Remember, it was sending on a certain path. So, for example, a left-right polarization would stay on the horizontal path, so undisturbed, coming horizontally and going through, and it would reflect the photon with state of polarization up-down. So here you could think of polarization, the state of polarization, as the control qubit, and the target qubit would be the state of momentum. Okay, so, and that would be exactly the same behavior as we described. Now let's talk about costs. So we will need to cost our circuits throughout the course. The course that this course is about the complexity of algorithms, okay? So the cost of the algorithm and what makes an algorithm inexpensive, what makes it expensive. So here I will present 3 ways to look at the cost of the same circuit, okay? The first way, and perhaps the most naive way, is to count the number of gates. The number of gates, ... in the gate set that you've chosen. So, okay, you've chosen a finite gate set. So for example, Clifford plus T plus Cnot. And you count the gates that only belong in this set. It's important because everything else could be a gate, right? If you so decide. So if you don't fix in advance a set of gates, every circuit could be 1 gate, right? But that is not realistic from an engineering standpoint. From an engineering standpoint, you have to imagine that we will try to physically realize as few gates as possible and then make circuits up to this very small set of gates. Okay, and now the challenge is how few gates can you do to realize a given circuit? So the G cost is counting the gates. That's a pretty obvious notion of cost. Now, another way that we can look at the cost is by saying how fast is this computation going to terminate? Okay, that is a very legitimate way to looking at the cost. So we will call that depth or D cost. And the depth is the number of gates, the maximum number of gates you see on each wire. So here it's easy, it's only 2 gates per wire. So the depth equals 2. Okay, but if I had more gates, for example, here, then the depth will become 3 because the one wire that has the most gates is the one that rules the depth. Okay, so if I have more, if I keep putting more gates on that first wire, then it will become that wire, and then the number of consecutive gates it has is the depth of the whole circuit. And so this obviously tells you that the amount of effort that you have to take, that you have to produce to go from the beginning of the circuit to the end of the circuit. Okay, so that is essentially proportional to the time that your circuit will take to execute. Okay, and we want that time always to be small as much as we can. Now, last is a more recent way people came up to looking at the cost is the dW cost, the depth times width cost. So what is the motivation for that? The motivation for this cost is to look at to sort of try to penalize idling qubits, the qubits that are on a wire where very few gates are being executed. So if you just count the number of gates, a wire that stays without operations for a very long time is not going to contribute very much. However, it turns out that most of the models that we have for fault-tolerant qubits, the ones that resist from the influence of the environment, they involve active error correction, which means that even if the wire doesn't have gates, there are sort of circuits that are going to be being executed at least regular time increments to preserve the information on the qubit. And what it means is this is costing you effort that is proportional to the time, which is, we said, the depth of the circuit. So by multiplying the depth by the number of qubits, we have a cost function that captures the cost of the qubits on which, even though not much happens throughout the computation, so they don't contribute too much to the G cost, they still will cost you a lot more compared to a circuit that has a smaller dW cost, okay? But there is a lot of discussions currently going on what is a good cost, okay? And this is not necessarily a debate that is completely over. But throughout this course, we will discuss the notions of cost at least using those three different costs that we've presented. And now for the subsequent modules 2, 3, and 4, we'll start looking at non-trivial algorithms for which quantum computers vastly outperforms with respect to those notions of cost, their classical counterparts. Thank you for your attention.